Welcome to this comprehensive tutorial on support vector machines, one of the most powerful and elegant machine learning algorithms. I'm your name, and today we'll dive deep into understanding how SVMs work, when to use them, and why they're so effective for both classification and regression tasks. By the end of this video, you'll have a solid grasp of the mathematical intuition behind SVMs and know exactly when to apply them in your projects. Here's what we'll cover in the next 15 minutes. First, we'll start with the fundamental intuition behind SVMs, what problem they're trying to solve, and why they're unique. Then we'll explore the key concepts like support vectors, hyperplanes, and margins. We'll understand how the kernel trick makes SVMs incredibly powerful for nonlinear problems. I'll show you the different types of SVMs and when to use each one. Finally, we'll discuss the advantages, limitations, and real-world applications of this algorithm. Let's start with a simple question. Imagine you have data points from two different classes scattered on a plane. How would you draw a line to separate them? You might draw several different lines, and many of them would work perfectly fine for this training data. But here's the key insight that SVMs bring to the table. Not all decision boundaries are created equal. Some will generalize better to new, unseen data than others. SVMs solve this by finding the decision boundary that maximizes the margin, the distance between the boundary and the closest data points from each class. Think of it as finding the safest place to draw your line. The intuition is beautiful. If you maximize the margin, you're creating the most robust classifier possible. This boundary is called the optimal hyperplane, and it's what makes SVMs so powerful. Let's define some key terms. The hyperplane is our decision boundary. It's a line in 2D, a plane in 3D, or a higher dimensional surface in general. Support vectors are the data points that lie closest to this hyperplane. They're literally supporting the decision boundary. The margin is the perpendicular distance between the hyperplane and the nearest support vectors. Here's something fascinating. Only the support vectors matter for determining the hyperplane. You could remove all other data points, and the decision boundary would remain exactly the same. Now let's look at the mathematical foundation. SVM is essentially an optimization problem. We want to maximize the margin, which mathematically translates to minimizing the norm of the weight vector W. The constraint is that all data points must be correctly classified with a margin of at least 1. This creates a quadratic optimization problem that has a unique global solution. The beauty of this formulation is that it's convex, meaning we're guaranteed to find the optimal solution. But what happens when your data isn't perfectly separable? Real-world data is messy and classes often overlap. This is where soft margin SVM comes in. We introduce slack variables that allow some data points to be on the wrong side of the margin or even misclassified. The parameter C controls this trade-off. A high C value means we penalize misclassifications heavily, while a low C allows more flexibility. This is your bias variance trade-off in action. Here's where SVMs become truly powerful. What if your data looks like this, clearly not linearly separable? The kernel trick is one of the most elegant concepts in machine learning. Instead of trying to separate the data in its original space, we map it to a higher dimensional space where it becomes linearly separable. The amazing part? We never actually compute this mapping explicitly. We use kernel functions that compute dot products in the higher dimensional space directly. Let's look at the most common kernels. The linear kernel is just the regular dot product. Use this when you suspect your data is linearly separable. The polynomial kernel can capture polynomial relationships. The degree parameter controls the complexity. The RBF or Gaussian kernel is incredibly popular because it can approximate any continuous function. It creates smooth, nonlinear boundaries. The sigmoid kernel behaves similarly to neural networks. Each kernel transforms your data differently, so choosing the right one depends on your problem's nature. Let's focus on the RBF kernel since it's so widely used. RBF stands for radial basis function, and it measures similarity between data points. The gamma parameter controls the reach of each training point. High gamma means each point has a smaller influence, creating more complex boundaries. Low gamma creates smoother, more generalized boundaries. Think of gamma as controlling how wiggly your decision boundary can be. SVMs aren't just for classification. They're excellent for regression too. Support vector regression, or SVR, works by finding a function that deviates from the actual values by at most epsilon. Instead of maximizing margin between classes, we create an epsilon tube around our regression line. Points within this tube don't contribute to the loss function. This makes SVR robust to outliers. The support vectors in regression are the points that lie on or outside of the epsilon boundaries. Parameter tuning is crucial for SVM success. For C parameter, high values create complex models that fit training data closely, but might overfit. Low values create simpler models that generalize better, but might underfit. For gamma in RBF kernels, high values create complex boundaries that might overfit to training data. Low values create smoother boundaries that generalize better. The key is finding the sweet spot through cross-validation. SVMs have several compelling advantages. They're incredibly effective in high-dimensional spaces, even when you have more features than samples. They're memory efficient because they only store support vectors, not all training data. The kernel trick makes them versatile for both linear and nonlinear problems. They provide a unique, globally optimal solution, no random initialization issues like neural networks, and they work well with small to medium-sized datasets. However, SVMs have important limitations. They don't scale well to very large datasets. Training time increases dramatically with data size. They don't provide probability estimates directly, only classifications. They're sensitive to feature scaling. You must normalize your data. Parameter tuning can be time-consuming, especially with grid search, and they can be slow on very large datasets compared to simpler algorithms like logistic regression. SVMs shine in many real-world applications. In text classification, they're excellent for spam detection, sentiment analysis, and document categorization. In image recognition, they're used for face detection, object recognition, and medical image analysis. In bioinformatics, they classify gene sequences and protein structures. They're also popular in finance for credit scoring and fraud detection. The common thread: problems with moderate-sized datasets where accuracy is crucial. When should you choose SVM over other algorithms? Use SVM when you have high-dimensional data, need high accuracy, and have a moderate-sized dataset. Choose logistic regression for large datasets where you need probability estimates. Pick decision trees when you need interpretability. Neural networks are better for very large datasets and complex patterns. Random forests are great when you want good performance with minimal tuning. The choice depends on your specific requirements and constraints. Here are key best practices for using SVMs effectively. Always scale your features. Use standard scaler or min-max scaler. Start with RBF kernel for nonlinear problems and linear kernel for high-dimensional sparse data. Use cross-validation for parameter tuning, but be patient. It can take time. For large datasets, consider using stochastic gradient descent variants like SGD classifier. Monitor overfitting by comparing training and validation performance. And remember, feature engineering often matters more than parameter tuning. While we won't code today, here's the typical workflow. First, load and explore your data. Then pre-process by scaling features and handling missing values. Split your data into training and testing sets. Choose an appropriate kernel. Start with RBF for nonlinear problems. Use grid search with cross-validation to find optimal C and gamma parameters. Train your model and evaluate on test data. Finally, analyze support vectors and decision boundaries to understand your model's behavior. Let's recap what we've learned. SVMs find the optimal decision boundary by maximizing the margin between classes. The kernel trick allows them to handle nonlinear problems elegantly. They're powerful for high-dimensional data and provide unique, globally optimal solutions. However, they require careful parameter tuning and feature scaling. They work best with small to medium-sized datasets where accuracy is paramount. The algorithm's mathematical foundation makes it both powerful and interpretable. To continue your SVM journey, I recommend implementing the examples we discussed today. Practice with different kernels on various datasets. Explore advanced topics like multi-class SVM strategies and online learning variants. Study the mathematical derivations if you're interested in the theoretical foundations. And most importantly, apply SVMs to your own projects. That's where the real learning happens. Thank you for watching this comprehensive guide to support vector machines. I hope you now have a solid understanding of how SVMs work and when to use them. If this video helped you understand SVMs better, please give it a thumbs up and subscribe for more machine learning content. Drop a comment below if you have questions or want to see specific topics covered. Until next time, keep learning and happy coding.